Okay, another common follow-up question is to interpret the gradient, which we know just means slope, and the p-intercept, which is really just your y-intercept of your model in the context of the problem. Okay. So your gradient is this guy, right? Your slope, 2.67. So I'm going to say m equals slope equals 2.67. And we do like to make sure that our slopes are always in a fraction form. And if it's not given to us in a fraction form, just go ahead and put it over 1. Because then we think about, well, what is a slope? It's rise over run. In other words, our change in our y's over our change in our x's. Well, what is our y values? Up here at the top, your y values are the price versus your x value, which is the mass, the weight, the amount that you're receiving of this maize. Okay, so that means for one mass, which in this case it's kilograms, so 1 kilogram of this corn meal results in 2.67 price, which is this ZMW price, your Zambian currency. So that's all it means, is that these two go together. For every one of those, it costs 2.67. So that's all it means to interpret it in the context of your problem, to understand that it means that that number over 1 represents for 1 kilogram of maize, it costs 2.67 Zambian currency. Okay, so you've interpreted the gradient. I recommend doing this. I do this every single time to be like, okay, so it's change in y over change in x. Y happens to be this, x happens to be this, and then I match it up. One of this, that of that. Okay, the p-intercept is your y-intercept, so 8.14. And if you think about it visually, that means that it's here at this idea of 0, 8.14. Okay. So that's 0 in terms of the x value, which is mass. So if you're not buying any of this maize, it would still cost 8.14, which is not logical, right? You wouldn't be paying to not buy something, but it's this idea of even the maize aside, the product aside, there's this set price of 8.14 that goes with this situation that's happening. And so there's this set amount that you have to pay no matter how much maize that you're getting. You have to pay this 8.14. Now, it could account for the cost of the bag that you're putting it in. It could account for the production or distribution cost, the people who are making it, the people who are transporting it, the gas that goes into it, the car, the labor, all of those things, right? So all of the other things that go into this maize are accounted for in this 8.14 basic cost. So you can say there is a set price of 8.14 ZMW for any transaction. If you really wanted to go above and beyond on your exam to show like, hey, I really know what I'm talking about, you can say this could account for the bag that the maize is going into, or this could account for the labor of the person who's at the stand of that day. So understanding that there's other cost prices that go into it that could be added on at the last minute. All right, we're going to use our model to predict the price of a 50 kilogram bag. Does your model overpredict or underpredict the actual price, and give a reason why? So we're going to use our model, which is just this guy. So we can do P of 50 equals 2.67 times 50 plus 8.14. Calculating that out, you should get like 141.64 to 3 sig figs. That means 142 ZMW. So for 50 grams of maize, we are going to be paying 142 Zambian currency. I do want to go real quickly and show you that you could then use, instead of doing it this way, you could also use your calculator and use the graph aspect of your calculator in order to do this. So I'm going to scroll back over to this graph that I had. That was my scatter plot. And if I go to a graph entry again, and if I go click function, it automatically pops up to F2. If it automatically pops up to F2, that means that there is something in F1, and I want to know what it is. So you scroll up. So notice that that red button right here meant that that's the button you would scroll or hit on your calculator. And then notice that this is the model that we wrote up here, 2.67 yada, yada, yada times x plus 8.14 yada, yada, yada. If I press enter on that guy, it graphs my linear regression with my scatter plot, which is cool because then you can see what you've got going on. If your IA requires you to have a regression equation with a scatter plot, this would be a great way to capture an image of what you did and put it into your IA. It's also great for you to be able to do interpolations with your model. So if I wanted to know what the Y value was when X is 50, I would go to here and hit trace and graph trace. Notice it's blue right away, which meant it automatically went to the blue dots, which is your scatter diagram. That's not what I want. So I'm going to click either up or down, and it's just going to shift which function I'm looking at. So now it's turned black because I hit down. I would have done the same thing if I hit up. And now I'm on my regression equation. If I type in 50 and then enter, then it brings me to what you can see. You can't see what I'm pointing with my finger. It brings you to this point right here. So at an X value of 50, the Y value is 142, which was what we found here. So there's different ways that you can do it. Here's how you could use your calculator. You could also just plug it into here. It says, does your model over or under predict the actual price? And so if you go back up here, realize that at 50, the actual price ended up being 140. So if our regression equation tells us that it's 142, that means that our model is over predicting the price. So the model is over predicting the price. One example of why this might be is that it makes sense that maybe the more product you buy from a stand, the stand owner is more likely to give you a discount, or maybe the scale is slightly off. So there's many reasons that you could write down here. I want you to think of one reason and type it out right now. Okay. Write down a reasonable domain for your model and give a reason for your choice. So this actually has one specific answer, and the one specific answer is that we cannot extrapolate from regression equations. If you remember, extrapolate means to gather from outside of the domain that your table has already given you, your raw data has already given you, right? So if this was our first point of raw data, this is our first point of raw data, this is our last point of raw data, anything to the left over here of the graph, anything to the right over here of that point, anything on the outside of those boundaries of the data points that we've been given cannot be relied upon in terms of their behavior. We can only interpolate, so we can only gather and predict from inside of those boundaries that our raw data has already given us, because we know what the patterns are in there. We don't know what's going to happen beyond those points. Maybe there's some point where the price shoots up way, way high because buying that much maize would be ridiculous, right? So if you wanted to buy all of the maize in Zambia, probably the price will, and the price per kilogram might shoot up. Or maybe if you end up buying a ton, maybe the price eventually kind of like lowers down a little bit because you're buying so much. So there's all sorts of different behaviors that could that are not accounted for if we're talking about extrapolation at the extremes. So we can really only interpolate, which means that a reasonable domain for this model is that it's forcing you to only look between what you've originally been given. So what we've originally been given in terms of our X values is between 5 and 50. And that is the only place that we can look at, except for that should be M, not X, for our model. And the reason would be that you would need to, you can only interpolate. Extrapolation is unreliable. With that, let's talk about a few other things that could possibly go wrong when we're talking about regression equations. Let's go to extrapolate first of all. We cannot extrapolate. Extrapolation is unreliable. We can only interpolate. Okay, so that's one warning with regression equations. Another warning is that we cannot predict x from y. So what we've been doing so far with this regression equation is that we've been given an x and asked to predict y. And this is saying if we're given a y and asked to predict x, in other words, working backwards, kind of like what we did with the cumulative frequency graphs. So remember in the cumulative frequency graphs, we were like, okay, well, we can like take the x-axis and go up and then shoot over to the y-axis. Or we can start on the y-axis, go over to the graph, and then shoot down to the x-axis. We could gather information from either side of that graph. With regression equations, we can only go one direction. Given x, what is y? The reason being is that this regression equation is created with the specific data points that you've put in, saying that these data points are x and these data points are y. And if you were to flip around what goes in for x and what goes in for y, your regression equation might not match up with what the idea of the inverse of this equation is, right? So remember that the idea of swapping your inputs and your outputs is an inverse equation. And so really when you're working backwards on a graph, you're thinking about it as an inverse without actually finding the inverse. So you're like, okay, well, if I can plug in x and find y, then what if I know y and try and find x? You're dealing with this idea of it being an inverse equation. So here we cannot treat it like it has an inverse because the inverse might not be the same. The actual inverse equation of this model that we got here might not be the same as the regression equation that we got if we put in our x values as y values and our y values as x values, okay? I'll say it one more time, just in case it didn't make sense. That if I switched from my original table, what I put in for x and what I put in for y, the resulting regression equation would not be the same as the inverse of this regression equation that I already got. It might be different. It almost always is different because of how the regression equation is calculated. So that's why it's only one road, because the inverse might not be accurate. So we can only be given x and find y from our model. Okay, and also just remember that a model is only as good as the correlation. You can find a regression equation for anything. You could put in a no association scatter plot, find a regression equation, and your calculator will give you a regression equation. So you can make a regression equation, EQ for equation, at any time. But if you have a weak correlation, then your regression equation is weak. Okay, so make sure to keep in mind that if you're like doing a regression equation on a moderate correlation or a weak correlation, then your regression equation might not be entirely reliable.